Hi, everyone. Good afternoon. Thank you, Tom, for the introduction, the invitation, for putting this together. I'm super happy to be here and to see a lot of old friends and meet some new people as well. Okay. So my talk today, I'm a statistician, and this is gonna be like an old school statistics talk, but hopefully I'll give a new perspective on this old problem called PCA. I'll be talking about an empirical Bayes method to try to improve the behavior of PCA. So this is joint work with two wonderful students, Xingyi Zhong, who's in my home department of statistics and data science at Yale, and then Cheng Su is in the department of biostatistics at Yale. So it'll have an applied flavor, this talk as well. Okay. So the talk will be about principal components analysis. And as a running example of PCA throughout the talk, I'm gonna use this one. So this is an illustration of a PCA analysis of some genotype data. The data that we fed in is a matrix of genotypes for about 2,500 individuals. And what we did is to sample about 100,000 roughly independent genetic markers across the genome. These are called the SNPs. And then we did a PCA analysis of these genotypes. So what you're seeing here in the two pictures, what's plotted is a plot of the first versus the second principal component, and then the third versus the fourth principal component in this data. In each of these plots, there are 2,504 points, where each point represents the embedding of one of these individuals into this four-dimensional principal component space. So that's what's being visualized here. And when you do PCA for this kind of genotype data, it's well understood that the information that you can extract is the ancestry of these individuals. So here, these different points, these 2,504 points are colored by these 5 colors that represent the ancestries of these individuals. And you see that they separate quite nicely in this PCA plot, right? So principal components analysis is the predominant way in which people correct for this kind of population stratification in genetics when doing genome-wide association studies. So this example here, there's enough genetic information. We're using 100,000 of these markers across the genome to estimate these plots. There's enough genetic information being used here that these estimates here, I claim, are quite accurate. In fact, if we increase the number of SNPs we use by another 10-fold to 1 million, we get approximately the same picture. So I'm going to interpret this pair of pictures here as a sort of ground truth in this data set. This is the kind of ideal PCA analysis that we want. And to distinguish this from the kind of applications or settings that this talk will be about, I'm going to do the following experiment. So in this experiment, I'm going to take these 100,000 SNPs and just randomly subsample 1,000 of those. I'm only using 1% of all of that genetic information. And I do the same thing. I do a PCA analysis of that resulting matrix. And the pictures that you get are the ones that you see here, right? So they look like much noisier versions of what we had before, for the reason being that we're using much less genetic data to estimate these principal components. So this is the basic phenomenon that I want to address in this talk. The phenomenon is that if I have small sample sizes, in this case, the sample size is the number of SNPs, and I'm trying to estimate these principal component vectors in high dimensions, then they might suffer from a substantial amount of estimation noise. This is a phenomenon that's well understood in the random matrix community. And the punchline or the main point that I will try to make in this talk is that in many applications, the true principal components will have some strong underlying structure. And the goal of this talk will be to describe what's called an empirical Bayes approach to first learn this structure and then use this learned structure to improve the estimates of the PCs. So I'll tell you what is this approach, but let me just show you an illustration of what the results of the procedure would look like. If I were to apply this procedure on this subsampled data of only 1% of that genetic information, on these subsampled 1,000 SNPs, the estimates of the PCs that we obtain are what you see in this picture here. And if I compare these pictures side by side, so on the very left are the principal components that I'm calling the ground truth obtained from all 100,000 genetic SNPs. In the middle was this noisy estimate where I only used 1% of the data. And on the right is what I'm calling this empirical Bayes procedure applied to the same 1% of the data. Yeah. The question is, if we use 3 components, would it be sharper? I think it would look roughly the same. You mean for the outcome of our method? I think for 3, it would look roughly the same. Yeah, sure. But I'll explain why we do more components later. So somehow we want to exploit the structure that's there in a multi-dimensional sense across these four components. Yes.
Component 1 versus 2.
Uh-huh.
What if you did 1 versus 4?
Yeah, it's because I can't make a four-dimensional picture on the slides, so I decided to do 1 versus 2 and 3 versus 4. I mean, I think you would see similar looking kinds of pictures if you. Yes. Let's say you arrange the matrix so that rows are your individuals and then your SNPs are your columns. And what we're estimating are the left singular vectors in this case. So the embedding of the individuals into this four-dimensional space by only using a subset of the columns, 1,000 of the 100,000 columns. Yeah. Okay. Okay, so what I want to do in this talk is to just explain what is the method that we're using, how it works, what the ideas are. Chosen randomly, yeah, chosen randomly. I'll explain what is the method, and I'll show a couple more results applied to data. And then closer to the end of the talk, I'll talk about the relation between these ideas and the literature, right? It's a pretty well-studied problem of how to do PCA. So I'll try to orient this a little bit. But okay, let me start with what is this method and then show you some results. So there are three main ideas that are underlying this approach. The first idea is what we would call in statistics an empirical Bayes idea, and it's an idea of how to use empirical Bayes to estimate normal means. The second idea is incorporating some components of random matrix theory that give a quantitative understanding of what the sample principal components look like. And then the third component of this idea will be an iterative refinement stage using what are called approximate message passing or AMP algorithms. Okay, so I'll explain each of these ideas in turn. And yes, please do feel free to interrupt with questions if you have as we go. Okay, so what is empirical Bayes? Empirical Bayes in statistics, if you haven't seen this before, it's a fundamental idea that I can explain quite simply in the following way. If I'm solving many repeated instances of some inferential task, this might be estimating a parameter or it might be testing some hypothesis. I want to first learn the characteristics of this problem that I'm solving by pooling the data across all of these different instances of the task, and then using this information that I've learned to better solve each of these instances individually. And when I put it in this way, I think it seems sort of obvious or simple, but this is really one of the most profound ideas, I think, in the history of statistical inference. It really has profound implications throughout statistics. And so to illustrate what this means in a simple example, this is the kind of textbook example that I teach in all of my statistics classes, and it'll be the one that's relevant for the talk today. Suppose that the instance of the problem I'm trying to solve, these instances, is just trying to estimate a single number. So I have these d unknown numbers, theta 1, theta 2 through theta d. And for each of these numbers, I observe it with some noise. Let's say I observe a normal observation with that mean, and there's some noise level sigma. And now so equivalently, I have some unknown vector theta in RD, and I observe it entry-wise with IID noise. I don't tell you any information about theta, what it typically looks like, where it lives in RD. They're just arbitrary numbers. And I want to ask the question, how should we estimate theta, this vector theta? And so I think the basic answer that most of us would give is if I only have a single noisy observation for every coordinate, there's not really any averaging or sophisticated thing I can do. So I would just report the number I observe, x, right? So each estimate of theta I would be xi. And indeed, if I only had one instance of this problem, I just have a single number theta I and observe it with some noise, and I don't know anything about theta, I would probably estimate it by x. The empirical Bayes paradigm is suggesting instead the following kind of alternative procedure. Let me for a moment suppose that the coordinates of theta themselves are random, they're IID, let's say, and drawn from some prior distribution that I'm going to call pi. So I don't know what is this prior distribution pi, but if this is true, then I do know that the data I observe, x1 through xd, are distributed according to a convolution of this prior pi and this Gaussian noise. So the idea of empirical Bayes is that I can first try to estimate this prior distribution pi, from my observed values x1 through xd. And then after having estimated this prior pi, I can then go back and re-estimate each theta I using a Bayes shrinkage rule. I'm going to shrink my data x towards this prior pi. Yeah, for example, I can take the posterior mean, the expectation of theta given x, assuming that theta came from this prior pi, and I observe x. Yeah. And let me just clarify one thing. So if this assumption that the coordinates of theta themselves are random in IID, it's sort of just a it's not super, it's a philosophical distinction that's not really real in the sense that if I want, I don't need to assume any randomness for theta. If I have a deterministic vector theta in RD, then it's going to have some empirical distribution of its d coordinates, and you can interpret this procedure entirely as I want to first estimate what that empirical distribution of coordinates is, some deterministic object, and then I use that to refine my estimate of x. So in this sense, it's not really making any additional assumptions beyond theta as an arbitrary deterministic vector in RD. Okay. So let me illustrate this, this idea using the simple cartoon. The cartoon might look like the following. So suppose I get my data x1 through xd, and I plot a histogram of this data. And the histogram of the data looks kind of like this picture when I plot it. And suppose I know the noise variance per observation is 1. So this looks a lot like the picture that Sean showed this morning, actually, in his tutorial. And so what I claim is that if you see a histogram of your data, and it looks like this picture here, then what you should be able to infer about the coordinates of theta are that the distribution of coordinates of theta don't actually look like this picture, but instead the distribution of coordinates of theta might look something like this picture down here, right? So this is the same kind of setting that Sean was talking about this morning. The important distinction I'm trying to raise being that in that setting, we were talking about a stochastic block model where your vector had +1, -1 coordinates that indicated the community memberships. What I'm saying here is that even if a priori I did not know that this vector is supposed to encode some community memberships that have +1, -1 coordinates, if I just look at my observed data in that first picture, I should be able to infer that the true theta indicates some kind of community structure. So I should be able to draw this inference and learn that the distribution of coordinates of theta looks something like the picture down here. Now, once I've learned this picture down here, I can go back and try to estimate every single coordinate of theta, and I can do it much better than just using the observation x. For example, if I observe a value of x at around -4, then my belief is probably that it came from a theta with value -2, so I might shrink that heavily towards this value of -2. And so this empirical Bayes estimate would end up shrinking each of my observations xi towards these two values +2, -2. And hopefully you can intuitively convince yourself that the resulting estimate will be much more accurate for estimating theta than just using the vector x. This can all be formalized as a concrete mathematical theorem saying that the mean squared error of that estimate is much improved over just using x itself, even though I really haven't made any additional assumptions on what is theta, what is the structure of theta. So this is the idea that we call empirical Bayes in statistics. The specific implementation of this idea and how you want to do the estimate, there are different kinds of procedures that have been developed out there. The one that we're going to use in this work that I'll talk about in the talk is what's called the Kiefer-Wolfowitz nonparametric MLE. The idea is just the following. So it's just a question of how you want to do that deconvolution to estimate the prior. And the NPMLE does the following. So we write down a maximum likelihood kind of problem where I take the convolution, does this work? Yep, I take the convolution of pi and this Gaussian noise, and I look at the log likelihood function. I sum that over all my samples. And then you solve this infinite dimensional maximum likelihood problem over all possible probability measures pi on the real line. Okay. And this approach was proposed in the 50s by Robbins and Kiefer-Wolfowitz. It's been studied for quite a few decades in statistics. It's understood that this maximization problem is well posed. There will be a maximizing measure. This measure will be a discrete. F is it's the density of this convolution. So I take I take my prior pi, convolve with this noise. That's what I believe my distribution of x should be. And this is just the log likelihood function according to that. And I maximize this over all measures pi. So at least conceptually, you can do this. It's known that this maximizing pi is the measure with discrete support. The atoms of the support will be data dependent. And in practice, I can't really implement usually an infinite dimensional maximization like this. So one kind of crude approach that people do, and the approach that we're going to use, is to just discretize the support of pi. So I take this space of all probability distributions and let me just fix some really fine grid of points along the support. And I fix those support points. And what I'm trying to estimate is just a weight for each of these Dirac delta masses of what is the weight on that point of the support. And this you can turn into a convex optimization problem and solve efficiently. So this is the approach that we're going to use. And I'll say a little bit more about exactly how we discretize the support later in the talk. Okay, so this is the first component of the idea. It's empirical Bayes. And the connection of this idea to the PCA problem, one way that you can think about this is the following. So in PCA, what is the repeated task that I'm trying to solve? What are these instances of the problem? One way to think about it is that each instance of the problem is figuring out where to embed a certain one of these individuals. So I had 2,500 or so individuals, and for every one of them, I wanted to put them somewhere on this four-dimensional plane. And these are the repeated instances of this task that I want to solve. And so what we're going to do is to use this empirical Bayes idea to first learn a prior distribution over the true principal components, and then use empirical Bayes to shrink towards that prior. Okay. This perspective, I think it's surprisingly new. So the first paper I'm aware of that explored this perspective, the PCA, was a paper by Wang and Stevens a few years ago in 2018. And Wang and Stevens were statistical geneticists, who I think were looking at applications quite similar to the ones we were looking at when we came about this idea. Okay, so the second component of the method is something that I think would be familiar to most people in this audience. It's some component of random matrix theory. So let me now write down a concrete model for my data. And for simplicity here, let me write down a rank 1 signal plus noise model. Okay, so suppose that I have some data. It's M by D and rows and D columns. And suppose that it consists of a rank 1 signal component that I'm indicating here. And then let's say some IID Gaussian observational noise, W. Okay. And what we mean by PCA, the principal components, I'm going to denote by U hat and V hat PCA. They're the sample PCs of this. So it's just the sample singular vectors of this matrix Y. And my goal in this task will be to try to estimate the true vectors U and V. So the body of theory that we're going to appeal to is this body of theory around this BBP type phase transition, which says the following, that if I consider an asymptotic limit in high dimensions as n and d go to infinity, proportionally, let's say with the proportionality converging to gamma, then we can quantitatively predict what is the accuracy of the sample principal components for the true components, right? So if I look at the inner product between my sample PCs and my true PC, so on the left and on the right, that there's essentially a deterministic prediction for what these inner products should be. And it depends only on two things, this aspect ratio gamma for my model, as well as the strength of the signal. So what is the singular value of the signal in my data, right? And this kind of theory, it was summarized quite well in this paper by Benaik, George, and Nadakuditi. They drew this picture that I'm taking from their paper. There's a cone in high dimensions. You have a true principal component vector that's at the center of this cone. And with high probability, your estimate of the PC will lie somewhere on the surface of this cone. And the angle of that cone reflects exactly the accuracy of your PC estimate, right? So the larger your true singular value, the smaller the angle will be for that cone, and the more accurate is your PC. So the specific quantitative forms of exactly what this function is, they're not going to be important for the talk, so I'll just call them mu star and mu bar star. Okay, great. So if I think about this picture of this cone, I have this vector and I have some vector on the cone. What this means on a coordinate by coordinate wise sense, and in a per coordinate sense, is that the coordinates of my sample PC estimate, my sample singular vector, should look like Gaussian noise around my true coordinates of the vector, right? So in other words, if I take each coordinate V, let's say, of the true PC, then my sample coordinate will look approximately like a Gaussian model where I scale V by some constant. This constant is exactly this inner product of that cone. And it'll have a coordinate-wise variance sigma squared, which is 1 minus the square of that constant, right? And so if I have this approximate Gaussian law, then connecting this to this empirical Bayes idea previously, this provides a precise quantitative connection between this PCA kind of problem and this preceding normal means model that I was talking about in this empirical Bayes context. And so the idea of our method is that we're going to estimate this principal component vector V by first learning a prior distribution for the coordinates of the true PC, and then applying an empirical Bayes shrinkage, for example, the posterior mean estimate, to shrink towards that prior. So this is the idea. Okay, so this body of theory is developed under it's a simple mathematical model, right? It's a low rank plus noise. So you should take it with some grain of salt. There are applications where this body of theory seems to be exceedingly accurate, and this includes this kind of genotype setting that I'm using as an example in the talk. So to illustrate this, what I'm showing you here are 4 histograms. Each of these histograms is a histogram of the coordinates of that singular vector. So I showed you these top 4 PCs earlier. If I look at the coordinates of those singular vectors at this subsampled size of 1,000 SNPs, so the noisy coordinates, the histograms of those coordinates are shown in blue in these panels. The U, yeah, so in this context, what I'm trying to estimate, let's say, are these vectors U. U is a vector with 1 coordinate per individual, and that coordinate represents in this PC dimension where that individual lies. So in this example, I have 4 left vectors U, and the coordinates of those 4 vectors are exactly those pictures that I showed earlier. So what I'm showing you here are just the marginal histograms rather than this PC1 versus PC2. I'm just showing the coordinates of those vectors. And it's the noisy coordinates. And what you're seeing as these black curves is this theoretical prediction from that body of theory I was just describing. So what we did is to take this ground truth computed by using all 100,000 SNPs. So that is some much tighter distribution with less noise. And I computed from this body of theory the angle of that cone and convolved that ground truth distribution with the expected level of noise that we should see from that random matrix theory prediction. And the black curves that you see here are the density functions of that convolution. And what these pictures are showing is that at least for this kind of genotype data set, the predictions of this mathematical theory are actually quite accurate for the data that we observe. So this is the second component of this empirical Bayes idea. And then the third component of the idea of the method is this component of iterative refinement. And to motivate this third component, let me maybe ask the following kind of naive question. Suppose I've used this procedure I just described to estimate the PC on one side. Let's say I estimated this vector V using this idea. How should I estimate U, the PC on the other side? And the way I've posed this problem, everything's completely symmetric. So one answer is I can apply the exact same procedure to estimate U on the other side. But if you think about this question a little bit more, you might realize that if I think I have a better estimate of V, which is the PC on the right side, then another thing I can do is to pass it through this matrix Y, take Y times V. That should give me a less noisy version of my U on the left side than the original sample PC. And I can try to denoise that thing instead of my original PC vector U hat, right? So we can try to apply something to Y times V instead of to U. And then having obtained this estimate on the left side, then I can think, well, maybe I can pass it back through Y to the other side. I obtain an even less noisy version of the vector on the right side, and I denoise that, and I get a better estimate on the right side, and I can iterate this process. So this method that we're calling EB-PCA does this kind of iteration. And the specific way that it does this iteration is using an algorithm that's called approximate message passing in the literature. It's an algorithm where I initialize on one side with the sample PC, let's say VHAP-PCA. I do some empirical Bayes denoising in the manner I described, and then I pass it through Y. And then on the other side, I do some empirical Bayes denoising of that vector. I pass it back through Y transpose, and I iterate this back and forth. And this is a very natural algorithm, except for this detail that I've omitted to describe just a moment ago, which is that in every iteration that I pass through, I subtract a certain correction of bias on both sides. This is a characteristic of what we call these approximate message passing algorithms. And this correction of bias, I can maybe try to explain a little bit more later in the talk, but it's a correction that that will preserve this approximate normal means model for the individual iterates of this algorithm, right? So the claim I made at the beginning was if I just take the sample principal component, it looks like a Gaussian noise model around the true PC. If I do this iteration once in some naive way, my next iterate might not look like just Gaussian noise around the true PC, right? And these corrections of bias are certain corrections that we can introduce to preserve this Gaussian approximation to the distribution. Okay, so this is what I was just saying a moment ago, and this algorithmic idea is well studied in the literature, and in this kind of PCA application, it goes back to the work of Ragan and Fletcher in 2012. Okay, so these are the three components of the idea, and if I want, I can state a theorem that formalizes some of the guarantees of this method. So suppose that I have this rank 1 signal plus noise model. Suppose that the coordinates of my left singular vector and the coordinates of my right singular vector, they come from some prior distributions. I'm calling pi star and pi bar star, and let's say my noise on top of this has Gaussian entries. Then what we can guarantee about this method is that in this high dimensional asymptotics as n and d go to infinity, first of all, the method is going to give a consistent estimate of these unknown prior distributions over the space of all possible probability distributions. And then furthermore, every single iteration of this passing back and forth, it's going to be described by an approximate Gaussian model, where each iterate on the left and right side will be approximately a Gaussian model around the true PC with some variance. And as you iterate back and forth, the size of that variance is going to decrease, and you're going to get less and less noisy observations of your ground truth. And the manner in which these variances change and decrease are described by what's called the AMP state evolution. Okay, so to say this a little bit more informally, what this is saying is that the iterates of this algorithm are going to be asymptotically described by these normal means models, which means that in every iteration of the algorithm, I can apply this empirical Bayes idea to get a better estimate of the PC than my original sample pieces. Okay, so these are the three components of the idea. And getting back to some of the questions that were asked earlier in the talk, so I've described these components of the idea in this setting where I just have a rank 1 signal plus noise model. Obviously, for a lot of data applications, we have a signal that's not rank 1. It's some higher rank kind of thing that we're interested in. And in a lot of applications, I want to claim that the kind of joint structure, the prior structure that you observe in the data for this leading low rank component is something that's much stronger when you look at it in a multivariate sense, right? So if I look at this genotype data that I've been illustrating, if I look at this a single principal component at a time, that would be these 4 marginal histograms that I showed earlier, which have some semblance of structure to it. But if I look at these sort of bivariate plots, or if I could plot in 4 dimensions and actually visualize this thing in 4 dimensions, you would see that the level of structure in 4 dimensions is much stronger, much sharper than what you get if I just looked at this one PC at a time. Okay, so what this suggests and what we do is that we apply these ideas in a multivariate context. So the analysis of the data that I showed earlier, what we did is actually to learn a multivariate prior distribution over R4. We learn a distribution in 4-dimensional space that reflects the structure that you see in this picture, and we do this empirical Bayes shrinkage towards that structure.
Should go be to see that we get some samples together, that the purple on the left side, on the same samples to be.
Okay, so the colors here are indicating the ancestries of the individuals. And if I do a piece, it's not true that every single principal component is necessarily going to help us distinguish every division of ancestry, right? So the hope is that, So the goal is maybe if I take a much noisier data set of the form of those kinds of point clouds that I saw earlier, and I only had that data, let's say I did not have all 100,000 SNPs, can I estimate the principal components and get an estimate that looks more like this picture, right? Can I get improved estimates of the principal components rather than just using these sample PCA estimates? Right, so if I had a data where if I do a naive PCA analysis, let me go back all the way, it looks something like, oops. If I had a data set where I do a PCA and I get this kind of picture, is there some hope of improving the estimates as represented by these pictures? Right, I want to get an estimate of the underlying principal components that's less noisy than this one here. Right, and then the claim is that in a lot of applications we can, by first trying to learn what is the underlying structure, right? This should be some Gaussian noise on top of a true underlying structure. My goal is to estimate that true underlying structure. No, there's no, the left picture, I'm just using 2 pictures to visualize the first 4 principal components. No, I'm going to interpret both pictures at once. So if I really want to use this picture, let's say to distinguish ancestry and to say separate the people of African ancestry from the people of East Asian ancestry, I would use the information from all 4 of these principal components. And in genetics analyses, it's common to use 40 to 100 principal components and use all of these simultaneously to get a very fine-grained division of ancestry. Yeah. Yeah, it's possible. You might have some PCs that, for example, these top 4 PCs that you're showing here do a reasonably good job of separating this ancestry. If you zoom into Europeans and I want to separate the Northern Europeans from the Southern Europeans, or I want to do more refined things, I might look at further PCs, and those might give me information to further delineate. Thanks. Okay, let me zoom forward. Okay, so I think I've explained basically all of the components of the method. Maybe minus one detail, which is how we do this discretization and the estimate of the NPMLE. I mentioned that we use this gridding idea before. If we start looking at more and more dimensions, I mentioned we're estimating this prior in 4 dimensions. If we increase that to something like 10 dimensions or something like this, it becomes harder and harder to just grid the support of the distribution in R4 or R10. So the approach that we use is what's sometimes called the exemplar approach in the literature, which is to take the observed coordinates of the sample PCs as the support of the prior. The intuition being that the sample PCs we hope will form some point cloud around where my true prior support is. And if it's the dense enough covering of that true support, then I can estimate the weights associated to the coordinates of the sample PCs. So this is the way we do the discretization in dimensions like 4 or 5. Okay, so let me maybe give one illustration of this difference between looking at a bivariate structure versus looking at just a marginal structure. Here we're doing a simulation where I have a rank 2 signal plus some noise. And if I look at the left PCs of this rank 2 signal, the way I've generated them in the simulation is that those coordinates form a circle. Right, so I look at the 2-dimensional plots and those 2 coordinates give me this circle. And we're simulating it in a setting of enough noise where if I just do a naive principal components analysis, the estimates of the PCs that I get would look something like this. And the axis labels give some indication of a quantitative indication of the error. And if we apply this kind of empirical Bayes PCA idea separately, like marginally to each of these coordinates, the estimate that we would get would look something like this. It looks kind of artifactual with these kind of square kind of structures. And if I do a joint analysis where I try to learn this full bivariate prior and then I shrink towards that prior, I get PC estimates that look like this, and they're much improved. Okay, so let me summarize the method then in a nutshell. I have a data matrix Y, and let's say I'm interested in some number K of the top left PCs and the number and of the top right PCs. The method is the following. We're going to estimate the parameters of some K-dimensional normal means model that describes the behavior of the sample PCs on one side. This is given by some asymptotic prescriptions of random matrix theory. And this will be based on the sizes of the signals that I observe in Y, so the observed singular values as well as the dimension ratio of the problem. Having estimated this normal means model, we're going to apply this Kiefer-Wolfowitz NP-MLE idea based on this approximating normal means model to get a better estimate of the PCs on that side, right? So I'm going to learn some joint prior for the rows of the PCs on one side, and then compute an empirical Bayes estimate of those of that PC vectors. And then I'm going to iterate. Having obtained that estimate, we'll pass it back and forth through Y and iteratively refine the estimate on both sides. Okay. And the specific way we do that iteration is again based on this kind of state evolution given by AMP. Okay, so I can show you a couple more examples of this in practice. So this is an example that's kind of similar in nature to this 1,000 genomes example I showed earlier. It's also a genotype matrix. This is from the HapMap 3 project. We're doing a PCA analysis. Here we have about 1,400 individuals, and we've taken about 140,000 genetic SNPs. And again, if you do a PCA analysis, what you get is a picture that delineates the ancestries of these individuals. So here in this picture on the left, I'm again plotting the top 4 PCs in what I'm calling the ground truth, which is using all of this genetic data. In the middle, I'm performing an experiment where I subsample this down to only 5,000 PCs. And if this was just the data set that I gave you and you do PCA, you would get these kinds of estimates that you see here. And on the right are the outputs, are the estimates for this empirical Bayes approach, where we first learn the prior and shrink towards that. And because of the way we're setting up these examples, so one reason why I'm looking at data of this form is that we can do quantitative validations, right? Because I have this, this full data set by which I can compute a ground truth, I can quantitatively measure how accurate are the estimates of these different approaches. These tables here are summarizing these comparisons on the 1,000 genomes data and the HapMap data that I showed for various amounts of subsampling. So if I subsample down to 100 or 1,000 or 10,000 SNPs, so we can compare the estimation accuracy. And a summary of these tables is that we're getting about a 15 to 50% reduction of the estimation of error, of the estimation errors over naive PCA. And the amount of reduction depends a little bit on how strong is your signal. Okay, and I'll leave you with one final application, which is this picture. So in most of the kind of data sets that we're developing this method for, it's not of the nature where I have a huge amount of information on one side to get an accurate ground truth. So in most of these data sets, I don't know the ground truth. I just do some PCA, I get some estimates. So this is maybe one application of this form. It's not for genotype data, it's for gene expression data from single cell RNA-seq. What you're seeing here is a PCA analysis of about 2,600 single cells and about 14,000 gene expressions. And what I'm plotting on the left here are plots of the first 3 this time, the first 3 principal components, 1 versus 2 and 2 versus 3. And these points, so each point represents a particular cell, and the colors are indicating the cell type of that cell. So they're colored by the different cell types. And in this data, if I just do a PCA analysis, I don't have a ground truth. I don't know what the ground truth looks like. I would get these 2 pictures. And if we apply our method instead, this empirical Bayes idea, we would get these 2 pictures on the right. And it looks like the estimates that we're getting are removing a good amount of this additional high dimensional noise from the naive PCA analysis. I can maybe point out one particular detail of these pictures, which is that if I look at, let's say, the yellow and the orange cell types in this picture, then in this scatter plot of PC2 versus PC3, they kind of lie on top of each other. They're quite separated in principal component 1. So the way you should visualize this is that in 3-dimensional space, I have these 2 separate point clouds. But if I project down to these 2 particular dimensions, they project on top of each other. And in the estimate that we get using our method, they're not projecting on top of each other. So what's happening is I'm learning the underlying prior in 3-dimensional space. And after shrinking towards this prior, the supports of that prior are actually not coincident on each other, right? So after I shrink and do the projection, we see that there are indeed these 2 distinct cell types in this data. Okay. Am I out of time, Tom? Okay, I was gonna say a little bit, let me just say one thing about relation to other methods to give some credit to some previous work. So I'll say quickly one thing about this method. So there was a previous method that I alluded to earlier by Wang and Stevens. They called it empirical Bayes matrix factorization. it's a method of a similar flavor where they were also trying to estimate some empirical distribution for the PCs and do the shrinkage. The way they formulated this method is based on a variational Bayes approximation. So they're in variational Bayes, you want to do posterior inference for these principal component vectors, and you approximate that posterior distribution by product measures in a way to minimize this KL divergence. And what they proposed is to try to jointly estimate both this posterior approximation as well as the prior distributions on the original PCs. So another name that this goes by is you can view this as an EM algorithm, where for the E step of the EM algorithm, you're using a variational approximation to approximate that E step. So it's called variational EM as well. And if you look at the quantitative forms of what you get from this kind of algorithm, it looks kind of similar to this EB-PCA idea that I was describing, except that you don't have these AMP kind of Onsager corrections. And the quantitative details behind how much noise you're assuming in this Gaussian model in every iteration of the algorithm is different. So it's not based on this high dimensional theory. It's instead based on some more heuristic prescriptions by using a naive mean field approximation. And the difference with EB-PCA is that we're using aspects of high dimensional theory to give a theoretically exact prescription for exactly how much noise you should be removing in every iteration. There's a deeper connection between these ideas, which is that these AMP algorithms, one way to view them, so I can think about it as an iterative algorithm, but I can also ask the question of what is the objective function that I'm trying to minimize in this iterative algorithm, or what is the fixed point that this is trying to converge to? And what's known is that this AMP approach, one way to think about it is that it's trying to solve a system of mean field equations that gives a more exact approximation to the true posterior distribution than using the naive mean field approach. So this correction term that you saw in the iterative AMP before, they're related to what's known as a tap correction in similar models of spin glasses in statistical physics, where when you're studying these high dimensional systems of interacting variables, there's a certain aggregate weak effect of dependence across these variables that you need to correct for to get an asymptotically exact approximation of the free energy in these kinds of models. And what's built into this AMP-based approach of iteration is this correction of the free energy. So the difference between this and something like this naive mean field approximation is that in settings where you have a bounded signal strength S, so these settings where your signal does not overwhelm the noise, this method that we're proposing is based on an asymptotically exact theory behind approximating the posterior means and behind approximating the free energy. Okay, I should probably stop here and not take more time, but thank you for your attention.